Okay, everybody, we are coming down the home stretch. On the way. I see the finish line coming in just a couple hours or so. Just a few hours down the road. Alright, if I can have your attention again. I'll just wait until it gets quiet here. Hello? Hola? Going back to Spanish, huh? Oh, you were? I can wait till we're done. Alright, let's get started. So we picked up on this area here. I'm not going to go through everything else that we just, I already went through this morning. However, to continue on with the concept, we're going to finish this lecture, then we're going to have an SQL exercise we're going to do, and then we're going to have some recap at the end about some assignments and stuff that you'll have to do during the break and a midterm, and I'll talk about all that stuff after we get done. So that'll be the second part of today's lecture. Do you have a question or are you just stretching? Just stretching, okay. I'm going to stretch too, okay. Defining a database scheme. So, a database scheme comprises of declarations for the relations or tables. So, going back to this concept of a schema again, defining a database schema, we're looking at declarations. By this, according to this definition, it's declarations of the relations or the tables of the database. Many kinds of elements may also appear in the database schemas, including views, indexes, triggers, and that we're going to introduce later. I'm actually going to talk about views and indexes, or probably just views today or right now, and then later I'll be talking about indexes and triggers. So declaring a relation, as I mentioned before, everything can be done in SQL. So here's the simplest form. Is to use a create table command and a create table with the table name and a list of elements. Also, you may remove a relation by going drop table. So drop table works too to remove the table itself. Delete table deletes everything inside of the table. Drop table removes the table. Truncate table removes everything, the table and the data inside of it. So it's kind of three different ways of doing it. So we have elements of the table declaration. So the principal element is the pair consisting of the attributes and the type. The attributes are the attributes that we get in the entity relationship diagram. So when we do those diagrams, we're supposed to be listing out, like for the book, ISBN number, for the catalog or sales or order, quantity and stuff like that. So those are considered the attributes that turn into the columns. And we can define them with the create table command. So this here actually is just the basic fundamental syntax of the command. When we create it, the most common types are used are integer, int, or integer, which are synonyms of each other. Your database application is going to be determining which data types are available. Actually, Oracle uses the word number. So don't take this slide set to fact that, oh, int is not working. Well, number might work actually for Oracle. And then in other databases, you're going to get slightly different data types as well. The data types themselves are pretty much the same. The wording, the way they're labeled, can vary. So we have reals or floats, character, variable character 2, different namings for it. Depending upon if we're going to define the field as being a string, a character, a real, something of a float value, or something of that nature. So create table cells in this particular example, where we have the bar, beer, and price. So what we're going to do is create, this is an example of the sales table from the same beer, bar, Frequence, and Sally, and Fred, and all those other people I was talking about earlier today. Same people are here again, same tables, but this we're seeing how the tables are actually created. So if you wanted to, you could actually take this slide set, just create all the tables, run all the queries, and you'd see how everything was actually put together. If you wanted to, but you don't have to. So here we have create table cells. We have our three items, or three attributes that appear in the sales table. Bar is a character of 20. Beer is a variable character of length 20. This is the length. And then price is a real. Some people are wondering, well, why do we want to use character 20 and then variable character 20? Well, there's actually a slight difference. In the character itself, there's a fixed length string of n characters. In a variable character, there might be a variable length string of up to n characters. What does that mean? Well, it's just a different definition in terms of the data type. Most people would actually just stick with one data type and use the variable character or variable character 2, depending upon what was being used in the database. And it's going to mean a similar thing. It depends on the range of values that you're going to be able to put in that particular attribute. We also have dates and times that we can declare. So the date and times are types. They're special data types in SQL. So the form of the date is, in this particular case, date by default is year, month, and day. And an example might be a date 2006, 07, 04, July 4th, 2006, or, you know, in terms of an example. The time is in the form of the time value as hours and minutes and seconds. So an optional decimal point and the fractions of a second are also considered. So here we have time given in a hours, minutes, and seconds with a 0.5. So we have decimal point seconds, and which equals 2.5 seconds after 3:30 p.m., which is kind of interesting. So, in terms of declaring keys, this is where the database gets, where we put the database constraints into the tables, I should say, where the database kind of gets its integrity from. When we declare the keys, the attributes are a list of attributes that might be declared as primary key or unique. In most cases, as I discussed earlier in the weekend here, and in all cases we want to make a primary key when it really is a primary key, but if we don't want to declare it as a primary key, we can call it a unique key, and that actually kind of works in the same fashion. Similar, but not the same. So these each say that the attributes that are going to be declared functionally determine all of the attributes in the relational scheme. So there are two distinctions to be mentioned later in terms of those differences. Here's an example of how we would use it in an SQL query. So declaring a single attribute key. So you place primary key or unique after the type in the declaration. So we have create table beers, name, character 20, and we're putting the word unique here. We can have as many unique keys as we want. We can take every single one of these attributes and make them unique if we want. It will make it more difficult to put data into this table though, because everything's unique. So we probably want to use those sparingly, but only when we want something to be unique. But it's not necessarily going to be a key, it's just going to be declared unique. So we can also declare multiple attribute keys. So a key declaration can also be around the elements in a list of elements in the create table statement. So this is a single attribute key where we've put the keyword unique next to the name. And this is the single attribute that we're referring to. So what we're looking at here is this form is essential for the key that consists of more than one attribute. So it might be used even for a one attribute key. So here's the concept here, where we're going to take bar and beer and make them a key. So this is how we do a composite, by the way. So the bar and the beer together are going to be a key for sales. Which means if we put a bar and a beer in there, they have to be a unique combination for each one of the entries that we put in there. So one bar is going to be a bar, but the bar can only have Michelob, Bud Light, Bud, whatever the beer happens to be associated with each one of the bars. So it guarantees that we're going to have a key for each one of them that we can list out, and that this is going to be unique. So it puts a heavy-duty constraint actually on the table that will hopefully enforce the business rules associated with putting data into this table. So we have the regular old create table sales with the bar, the beer, and the price, and then at the end of it, and then we go primary key, and we don't have to say equals, we just say primary keys is bar, comma, beer. And that primary key gets created automatically for us. It doesn't actually show up as an attribute in the table. It just gets worked as a primary key, which means the table is going to be indexed on bar and beer together, and we can't put in the same bar-beer combination in more than one row of this particular table. So it definitely puts some constraints on it. So primary key versus the unique, just to recap on some of the stuff I've been talking about this weekend. The SQL standard allows the database administrator or implementer to make their own distinction between primary key and unique. As an example, some database management systems might automatically create an index, which Oracle does, which is a data structure to speed up the search, in response to the primary key, but not on the unique key. So it's not a bad idea to check the documentation of the database that you're using. Some, including Microsoft Access, actually indexes unique as well, which is kind of odd. You know, they index everything, or they try to. So there's some required distinctions. So instead of SQL requires these distinctions, or however, as standard SQL, this is again referring to standard SQL, there can only be one primary key for a relation, but several unique attributes. So we can only have one primary key. So if we're going to have a second, we're going to make it a unique attribute. And no attribute of a primary key can ever be null in any row. Now this is standard SQL. Some databases allow you to override standard practices, but standard, no null in any row, because you can't, because how can null be unique, or how can a null be a primary key? But attributes declared unique may have nulls, and may have been may be in several rows might have also nulls. So you can have null appear more than once, unless you turn it off. You can adjust all of these settings actually most of the time. And then this is one of them. 99.9% of the time you can actually adjust in the database to make the rule so that uniques can't be null, which is what I would do if I were enforcing the unique quality of this. Other distinctions on attributes. Two other declarations can make for an attribute. So we have two other declarations we can make for an attribute. Are not null and default. So when we say it's not null, it means that the value has to be, can never be null. It has to actually be a real value. Which, if you take this case here and you take your unique key and you say not null, that means you can't put null in there. So it makes it so it looks like and acts like a primary key essentially for the most part. A default value says that there's going to be a specific value that's going to be inserted if no value is inserted. So it can never be unknown or empty, that there will be some value that's going to be put in there. And the value is going to be something generic, actually. And here's an example here. We don't have any not nulls in here, but we have, if we did, we just put not null right next to it. So here we have create table drinkers, and the name is going to be a character of 30 characters, and this one's going to be the primary key. We got you on the attendance, by the way.
Thank you.
Your friend told me.
Actually, I forgot my jacket and then I went back.
It's okay. You're good. So address has a character 50. And then we have default. This is actually on the same line, but it word wrapped to the next line here. But this is address character 50. Default 123 Sesame Street, which is, you know, from Sesame Street. Yeah. So hopefully you guys know that Sesame Street. Yeah. Okay, good. And the phone is character 16. Not that knowing Sesame Street makes you any more American assimilated, but definitely Sesame Street.
So
but hopefully you don't have to know about Barney, huh?
Sorry. This like whichever there won't be any address for that. This will be the value for.
Yes, if somebody leaves the address blank, it will not be blank in the database. Instead, 123 Sesame Street by default will be inserted into that attribute value. So you can do a query on the database and see how many people live at 123 Sesame Street. And then, you know, 50 people. Well, no one's giving us our address. They're leaving the address blank. So usually people do that with phone numbers. They go 555, 55, 5555, you know, or something. Or they go 123 Street, Elm Street. Okay, that's from, what is Elm Street from? No, it's from Elm Street. It's from a horror movie. Nightmare on Elm Street or something, yeah. So you guys are pretty up to date on all these movies. Or movie, Sesame Street though is not a movie. Do you guys know Mr. Rogers? Yeah. Wow. All right. You know, there's generations in the U.S. that have never heard of Mr. Rogers. There's generations in the U.S. that haven't even heard of Sesame Street either. But those are younger people because they don't play it as often. Now they have like Barney and all that other stuff going on. So. I don't watch children's cartoons, by the way. Alright, so the effects of the defaults. Suppose we insert the fact that Sally is a drinker, but we know neither her address nor her phone number. We just know that Sally's a drinker because she shows up at the bar and she's on my potential buddy list. So we can use an insert with a partial list of attributes and it makes the insert possible. So the defaults make it so that we can have a not null field automatically populated by default information that will come in if we don't know that information. And we can still put Sally in the database even though we don't know her address or where she lives and we don't know her telephone number. So we can insert into drinkers name values Sally. And everything else in this particular table here, this is the drinkers table. If we put the name in and the primary key is the name, then the address is going to be set to here, to 123 Sesame Street, and then the phone number is going to be empty. So.
Yeah, phone number is not default.
No, there's no default created for the phone number, so it'll be empty. And hopefully we haven't put a not null on there. If we put a not null on there, it's going to make it impossible to actually put Sally in there. If we change it to null, then we can put Sally in here. And here's what happens if we change it so we can put nulls in here. So one row was created. We have Sally, and her address is 123 Sesame Street. And then the phone number is null because we didn't put a not null on there. So if we had declared phone number not null, then the insert would have been rejected, and we wouldn't have been able to put that row in there. So we can add attributes. So we might change a relational scheme by adding a new attribute or a new column by using alter table, the name of the attribute, add, and then the attribute declaration. So we can say alter table bars, add phone number, default unlisted. Not a good practice to do because if you have data in the database and you add a new attribute to the table, everybody who's already in existence is going to have nothing in there. But if we put the default to unlisted, all of the ones that are empty will be saying unlisted all the way down, which may or may not necessarily be the appropriate action, but we can go back and edit it. We can also delete attributes out of a table, and then in that case we're going to lose the data that's stored in that attribute. So if we remove an attribute from the relational scheme, we can say alter table, give it the table name, drop the particular attribute. So the example here is we don't really need the license attribute for bars. I guess originally someone was keeping the license number. Don't need it anymore. So instead we can alter table bars drop license, and then all that information is going to be gone. It is not backed up or anything, it's just gone. So it brings us to a new concept. So those are concepts in terms of related to creating the database tables themselves. So you can do everything using SQL. You don't have to use any GUI interface for anything. Then we have this concept of the view. So the view is a virtual table. So it's a relation that is defined in terms of the contents of other tables. So we can take a table, run a query on the table, save the query results as a view, and then we can just query the view as if it were a table. So it's called a virtual table because it doesn't really exist. It's a query result. And at any one moment of time, we can query it and we can create it and it's persistent, but it doesn't really exist. The underlying data is actually stored in the tables. Nothing's actually stored in the query or in the view. So think of it sort of like a saved query, and we can query the query. So it's declared by create view with a name as a query. So I'm going to have an example of this coming up. So in contrast, a relations whose value is really stored in the database is called the base table. So sometimes you'll hear the terminology, it's a base table or it's a view. The base table is the storage of the data, it's the actual table, and then we build the views from the base tables. So here we have a table called, a view called can drink. These are the people that can drink. So we have can drink, that's going to be drinker and beer. So in the view containing the drinker-beer pairs, such that the drinker frequents at least one bar that serves the beer, which means these people can drink. So create view can drink as, and then we just put a regular query in there. So here we have select drinker, comma, beer from frequents, comma, sales, where the frequents.bar is equal to the sales.bar. And this is one of the queries we looked at earlier today. It just says, give us a list of the people who frequent the bars, essentially, and who are going to be able to frequent the bar because they like the beer that's there. And then we can query the view can drink, and we can run a query on that. And here it is down here where we can say select beer from can drink, where the drinker is equal to Sally. So we basically took this query result, saved it into what was called a view, and now we're querying the view, which is a lot more easier to do than querying the underlying table. Will it be faster? Not really. Depends on how long it takes to create the view, because you got two views in one, or you got two queries in one. You got the underlying query that creates the view, and then you got the query that's on the view. Not as fast for the long run as just querying the table. But if you only give access and privileges to the view and not to the underlying table, you can restrict the data view. So you can't see all the data. Classic examples like HR departments. When you go in to look at your data, your profile and your information that's in the HR, that's actually a view that you're looking at. It's a query on the HR table that only has you in there. So it doesn't really matter what breaks on the application. You can't get to anything outside of you. So you might be able to see your information that you're not supposed to see, but you're never going to be able to see somebody else's information. So it's done for security reasons to restrict the data. So views have that kind of unique kind of side effect to them. So you can query the view just as if it were a table. There's no limit on the ability to modify the views in the modifications. Makes sense as long as the modifications in the underlying tables make sense. So what happens when a view is used? The database management system starts by interpreting the query as if it were a base table. Typically the database turns the query into something like a relational algebra statement. And then the queries that are defining any of the views used in the query are then replaced by the algebraic equivalent and then sliced into the expression tree of the query. The query is run essentially, and then that query result is used as the view result. And I'm waiting to see if this actually goes into it. It does not go into the restrictions, so I'm going to mention the restrictions not on the slide. As it was previously noted, you can use a table and a view in the same way, and anything you can do on the view you can pretty much do on the table, vice versa, but with a couple of different caveats to it. So views for updating, for viewing, for selecting is the same. For updating, for deleting, for modifying is different. If the view is using multiple tables, no possibility of you being able to update anything. If the view is based on a single relation, one single table, you can update it, which is interesting. So you have to be careful in terms of what you're going to design in terms of the interface. So if you create a view and the view is using multiple tables and you want the employee to be able to update their personal information, not going to work. So eventually you're going to have to give them access to the underlying tables because they can't do it through the view. Because imagine how complex that would be in order to take a finished view and then work backwards through the underlying tables. And what they're modifying might be in many different tables. So the query engines aren't going to bother with that. They're just not going to allow it. So you'd make a view on each one of the tables probably and have the updates happen on the single views versus the multiple combined tables. So here's an example of the view expression and how that works. So it's actually called a projection. So the projection for the beer table is going to be, or for beer, we're going to do a select, and this is the canned drink. This is the view, where the drinker is going to be equal to Sally. From the canned drink, we have this projection that's going to come back with the drink or beer combos, and it's going to be a join of the frequents and the sales table. So when we query the canned drink view, we don't have to worry about what's underneath it. We don't have to worry about that join on any of the other tables. It just works for us automatically. So database optimizations. Interesting to observe that we have optimized the query by transforming an algebraic expression to one that can make it much faster to execute than another. So key optimizations, you want to push the selections down the tree and eliminate unnecessary projections. So here are the projections. This is the query. This is a query. So, and you want to push the selection further down so it's at the last, or excuse me, up the tree, so it's happening before anything else. Because otherwise what you're doing is you're getting the first iteration of the results that comes back, and then you have to sort through that. So don't ask for it unless you want it. And then if you push the selection and you go, just give me this and not everything, then you have a smaller data set, so it runs faster in theory. So here's some optimization here where we have a projection on beer and we have a join. On the select here, we could push this down a little bit to change the query. So the select drinkers equal to Sally from frequents, and then combine it with sales. So notice how most of the rows are eliminated from frequents before the expensive join is occurring. So joins by default take up this more time than anything else. So that's why they're called expensive, because they are very time consuming to join one table with another. So you want to push everything down to the lowest level before you join, and then do queries on the join. Have a minimal join set. So foreign keys, local and global constraints, yes?
Yeah, for this view, do we have any kind of privileges that we are setting on this view?
Yes, good question. The same privileges that you can set on a table, you can set on a view. You can also set them in the database object itself. So the same access privileges when you grant, modify, grant, whatever it is that you're granting or revoking, work the same way as if the view were an underlying table.
And also, is there any lifespan of this view?
No lifespan. The lifespan of the view is from the creation point.
So
If the tables go away, the view will fail and give you an error message. But the view will outlive the tables. Until you delete the view, you've got the view forever.
So, but you said that it's a virtual kind of table.
Correct.
Then, if we are rebooting our system, in that case, this virtual table will go away. Right?
If you use a create statement in this particular case to create the view, you get an object component called a view that's saved in with the database system. And so when you reboot the computer or the server, it's still there. It's like creating a table. But the table is the underlying base storage. The view is a query. The view query doesn't run until the view is accessed. So you can create a bunch of tables, create a bunch of views, save the views, save the tables. 2 years goes by, someone removes a couple of the tables, but the views are still there. Someone runs a view because it's still there, and it crashes. And then you go, what happened? Oh, it's because the underlying tables are gone. The view doesn't know that.
So it's dependent on that. That's why.
Yeah, it's dependent on the runtime, actually. Until you use it, it doesn't even know if it's even workable. Which is kind of the same thing with the tables. You can create all the tables, put all the key constraints in there, get it all configured and running great. And then you start putting data in and you realize, oh, it doesn't work. Because the key constraints are going in a circle. And I can't put data into this anymore, or at all, because if I put data in here, it's going to violate that over there, it's going to violate that over there, which is actually a way of making too much control, too much access control, and you're limiting what can actually be done to it. And then in that particular case, you probably should just start over and rethink your key constraints. Especially as an example, you've put a constraint in that a value must be of a certain ratio between, or a certain number sequence between 0 and 10, and then you run out of numbers. And you go, well, what about 11? Can't put it in. Because I have this trigger or this constraint that I created that says it can't be past 10. Well, then you have to go through and delete the constraint in order for the tables to actually work, if that's the case. So, no, you can make it so it's impossible to put data into your database. Very easily, actually.
Like in calendars, Y2K.
Yeah. You can make it impossible. Yeah, I'm glad the Y2K stuff is over with, but that brought back a lot of jobs, actually. A lot of people got employment from Y2K. But it made it impossible to have a unique date. Or it made it impossible for certain things to happen. So you had to fix the database. You had to fix the logic of the database and the storage in order to correct the problem. Store more digits or to do something different in terms of the logic. So, especially when you did calculations. And actually, for a while, we had negative. You are negative 5 years old. Oh, really? You are negative this. You have negative $2,000 in your account. What? Everything went negative. Because it started from like a negative number instead of a positive number on the... Anyway, when they did the calculations on the 0, 0, and then go 0, 0, isn't that an error just in itself? Started time over again from the beginning. So, constraints. So a constraint is a relationship among data elements that the database management system is required to enforce. An example of constraints might be a key constraint. So kinds of constraints. We have key constraints, foreign constraints, value-based constraints, row-based constraints, and assertions. Assertions are kind of easy, actually, to think about. These are not triggers, but I'm going to talk about triggers towards the end here if I remember. So the constraint on a key says that the keys have to match, or that the keys have to be of a certain value or a certain range. Foreign key and referential integrity means that a key in one table has to match a key in another table. They call it a foreign key because it's not in the original table. Someone's talking. I can hear you more than myself. I'm sorry. All right, value-based constraints. Those are constraint values for a particular attribute. The value must be an M or an F. That's what that's referring to, or something of that nature. Row-based constraints, the relationship among the different components. So you can put a row-based constraint in there that says if you're a senior and your GPA is this and you've taken this number of units, then you can enroll in this course. Or if you've taken all the prerequisites, but if you can't, then you can't enroll in this course. A lot of universities use prerequisite requirements as value-based constraints in a row. So it knows whether or not you go in and you can't go in. Then they have to override it. And then they say, oh, okay, well, we approve this one, we don't approve this one. So you can actually enroll in something. So it's a relationship among all of the different components. It's sort of like a formula. And then we have assertions, which are SQL Boolean expressions that we make that come back true or false that we can use as a constraint to allow something to either be entered or updated into the table. So foreign keys. So consider the relation cells, and cells has bar, beer, and price. So we might expect that the beer value is a real beer. Okay, something appearing in beers.name, hopefully. Otherwise we're going to make up our beer names. So a constraint that requires a beer in cells to be a beer in beers would be considered a foreign key constraint. So we use the keyword references, and we saw this already in one of the other lectures, but references, we'll say that this key references that key over there, which means it must match identically to something that's over there. So within a declaration of the attributes, when only one attribute is involved, an element of the scheme as in foreign key, a list of attributes references a relation along with the list of attributes. We'll see an example of this coming up. So reference attributes must be declared primary key or unique. If they're not, they don't make for a good reference. Because then you're going to have multiple reference keys that come back. And if you're Oracle, there's going to be an error message when you try to create this database. It's going to say, I'm sorry, beer name is not a foreign key. Or it is not a key, is probably what it's going to say. So here's an example of doing it with an attribute. So we have create table beers. Name is going to be a primary key. Manufacturer is going to be another attribute in that table. And then we have create table cells, where we have the bar is going to be a character 20. And then we have the beer. Okay, here's the beer here. It's going to reference beer names. So beer name up here. This primary key is going to be here. This is going to be the foreign key down here. We can also specify it as a foreign key, and we'll see that in a few minutes. But in this particular case, we're using references to refer to this guy over here. We don't have to say anything about its data type or that it is a primary key at all. We just basically say we're referencing it. And then we're also adding price real into this table as well. So here we can do as an element. So this one here is as an attribute. We've added the attribute in. And here's the attribute that we're going to reference. Which means if we try to put something in this table and it doesn't match something over here, it can't go into the table, which is what that's going to do. So in terms of an element, we can create a table beers, and we're going to have a name and a manufacturer, same as before. And then we can create the table cells. That's going to have a bar, and it's going to have a beer, and it's going to have a price. But then at the end, we're going to say foreign key beer references beer name. So we're adding it in at the end. It's just two different ways of syntaxing it. So one's an element, the other one's an component of the attribute. It accomplishes the same task. Some people like this better because when you look at it, you go, oh, what is that foreign? Oh, foreign key, there it is. References beer. This one here is actually a little bit easier to do, I think, but it doesn't say the word foreign key on it anywhere. So you're looking through the documentation, where's my foreign key? Because luckily on the slide you're looking at a back-to-back. But what if the beers table was way on another page or something? You may not actually know that that's referencing something that's supposed to be a primary key. We can have as many foreign keys as we want in the table. In fact, the entire table can be foreign keys if we want. You can have more than one foreign key. Only one primary key, however. So we enforce foreign key constraints. So if there's a foreign key constraint for an attribute in the relation R to the primary key in the relation S, the two violations are possible. And the two violations are an insert or an update on R introduces values not found in S. So, or the deletion of an update in S causes some row of R to dangle. So if these two are supposed to be the same, and we modify this one or modify this one, we're going to have issues, essentially. So we can put rules and set rules in the SQL system to deal with these things. So action number 1, suppose R is the sales table and S is the beers table, and an insert or an update to sales that introduces a non-existent beer must be rejected. So number 1 option, just reject it, don't let it happen, don't let it come in, which requires you to go over and put the beer in first. In fact, that's what ends up happening with a lot of business rules. Especially you hear it when you're talking to people on the phone. Hold on, I have to add you into that database before I can add you into that database over there. So you get added into something so that you can be linked with something else. Or you go, how come I'm not in here? Oh, it's because you're not in here. And then they have to fix, and they're basically updating databases in a particular order so that they can get it to work correctly. Which means that the database is rejecting everything unless you put it in there in a right order. Or you can delete. So you can delete or an update that removes a beer found in some row or cells, handles it in 3 different ways. So here are the 3 possible ways of handling it. By default, reject the modification. The second way is cascade the change. So make this changes in cells. So you put a customer in and the customer doesn't exist, immediately the customer gets added to the customer database. And so now I go, okay, wait a minute, here we go. And you start adding the information in because both of them need to be created in order for the integrity rules to work. If we cascade the delete, we can delete the beer, deletes a row in one table, also deletes a row in another table. That would not be such a good thing. If you were a student at ITU and you were in the registration table and you decided to drop a class and you got deleted out of the registration table and then you got deleted out of the student table at the same time, not such a good thing. So it's the business rules that are going to determine which course of action would be the most appropriate. However, if you were a customer and you were going to order something and you canceled the order, maybe it should cancel the shipment and maybe it should cancel you out of the system so you don't receive all this junk mail, hopefully. So there's good ways of doing it as well. Or an update that says, update everything and cascade it, or don't cascade it, but basically change values that are associated so they do match. Or you could set to NULL, which means change the beer and then set the customer to NULL or something. Or change the cells to NULL. So sometimes you see stuff that gets nulled out and you're wondering, why did that get nulled out? I'm customer NULL because you got deleted. And so the database naturally dealt with it by substituting missing deleted stuff with NULL. So then you got referenced as NULL. So we have this concept of cascading. So to cascade as an example, suppose we delete the bud row from the beers and then delete all the rows from cells that have beers equal to bud. Then suppose we update the bud row by changing bud to Budweiser. Well, then we change all the rows and cells with beer is equal to bud so that they now equals Budweiser. So we can cascade the changes across the system. That would be nice if it was linked up and we were using referential integrity. Because if you came in and you changed your address, it should change it everywhere. But not everybody does cascading. So then you see that it gets shipped to the wrong address because you updated your customer information, but it didn't update anything else in the system. So all of your shipments that are coming to you are still going to the old address. That means they didn't have cascading turned on, and they dealt with it a different way. Or you can set to NULL. So suppose we delete the bud row from the beers. We can change all the rows in the cells that have beers equal to bud to be beer is equal to NULL, because we deleted it. That would be equivalent to changing your student account to student is equal to NULL. So, or suppose we update the bud row by changing bud to Budweiser. We would have the same change occur. Everything would be NULL because it would not exist anymore, which may not necessarily be the best way of doing it. So we choose a policy, and then we can set the policy with our SQL statements. So we declare a foreign key, and then we choose the policies set null or cascade independently for deleting and updating. So here's the syntax for it. We follow the foreign key declaration with on update, comma, delete, set null cascade, or something. So two such cases may be used. Otherwise, the default is to reject it. So by default, if you're violating referential integrity, your update's going to be rejected. So here's an example about not using the default, setting the cascade in the updates. So here we have create table cells with bar and beer and price and foreign key that references beer, another table. On delete, set to null, and then on the update, cascade. So if we change Bud to Budweiser, it's going to cascade that change. So everything that references that key is going to be changed to Budweiser instead of Bud. So, or if we delete it from one, it's going to set it to null in the other. So, which might be a good idea if you're like having an order that you deleted. And you have a shipping tracking information. Set that to null, which means it's not going to be used anymore. We also have attribute-based checks. So you can put a constraint on a value of a particular attribute. The check condition gets applied to the table, and it gets executed every time you try to insert or an update. So inserts and updates will trigger the checks, and the checks will actually kind of, keep your data consistent. So we do a check on a condition. It must be added to the declaration of the attribute. So the condition may be used, may use the name of the attribute, but any other relation or attribute name must also be in the subquery. So here's an example of a check. So we have a create table cells, and it has a bar and a beer attribute. And then for beer, it's going to say check. Beer is in, select name from beers. So the beer that we're putting in is actually a beer. So we could have made that check a reference, actually, and made beer name, referencing beer name. However, we didn't want to because this example we want to use a check. So instead of using a reference, we do a check. This is a little bit more time consuming because the check actually has to run a query. So is the beer in select name from beers? Well, that looks like a query that's going to be run every time you insert something into this table. You're going to run a query. And the query is going to essentially see if the beer is in the beer name. Depending on how big the table is, your insert might actually be slower and slower. Different than a reference. A reference is going to use the index. So a foreign key reference that's going to reference back to a primary key to make sure that the beer references beer's names is going to be faster because it's going to use the index and it's going to go yes or no. And then it's not running a query. It's basically doing a reference on the, and it's comparing the indexes to make sure there's a match. However, this one down here may not be possible with a query, with a reference from a foreign to a primary key. And this one here is price. We're going to call this, this is a data type real, and we're going to put a check on price to make sure that the price is smaller than or equal to $5. Because in this database, we're not going to allow beer to be sold for more than $5. So it's going to essentially do this price check here. And if it's more than $5, it's going to reject the entire row, which is actually kind of nice. This is not a trigger, this is a check that gets performed on the database. And it's a check on an insert or an update, actually. So the timings of the check, an attribute-based check is checked only when the value of the attribute is inserted or updated. Otherwise, it's not checked at all. So a trigger is the same kind of thing as a check, but it's a stored equation, a stored calculation that's put in as a trigger, and it's declared as a trigger, resides in the database, and you can run the trigger anytime you want. And the trigger can be run on any type of modification or once in a while. And then actually, it's just like a stored procedure, actually. It just goes through and checks things and makes sure that the database is consistent, converts things, does all sorts of scheduled maintenance and stuff like that. So it's more for automated of behavior. It's not necessarily for making sure the data that's coming in is actually correct. Because if you want to protect the data coming in, or preserve the quality of the data coming in, you're going to put it in the table. And if you put it in the table, you're going to use a check. So here's another example here. If the check where the price is larger than or equal to $5 checks every new price and rejects it if it's more than $5. A check here if the beer is in select name from bars or from beers. Not checked if the beer is deleted from beers, unlike the foreign keys. So if it's deleted, it's not necessarily going to find it. So it doesn't use, the checks may not necessarily work with the foreign and the primary keys. They're not an integrity check. It's a check on a value. So then we have row-based checks. So this is how we would tell if you've completed all your prerequisite classes and you're able to take the class, which means you can't get into the registration table unless you've satisfied this condition, this condition, this condition. Well, then that would be a combination of data that was in the same row that we were trying to upload or update into the database. So we can run that as a row-based check. So here we have a check on a condition may be added as another element of the schema definition itself. And the condition may refer to any attribute of the relation, but any other attributes of the relation require a subquery. And so the checks on an insert or an update only, same as the other checks. So here we have a row-based check example where we have only Joe's Bar can sell beer for more than $5. So instead of putting the check to see if the price is larger than or smaller than or equal to $5 on the price, which would be an attribute-based check, we can do a row-based check. We've added it to the table so that every time a row gets inserted into the table, if bar is equal to Joe's Bar, or the price is larger than or equal to $5, it'll go in there correctly. So which means Joe can sell beer for more than $5, but everybody else can't. It's not a row, it's not a column in the table. It's invisible, actually. But it happens every time you put data into the table. Which is scary because some people look at the tables and they go, how come the data can't go in? How come I'm not getting data in there? Because there's this check in there. You can actually find the checks if you look at the graphical tools and stuff. You can actually see the schema of the table. You can say, oh, look at that, there's a row-based check. And then you can modify the row-based check to tweak it so you can get your data in there if you're the database admin and you're having problems working with it. But usually it's put in here for a reason. It's to enforce business rules. And here we're enforcing a business rule because we've approved Joe's Bar to sell beer for more than $5. So we're going to let that happen, which is going to violate all the other rules usually. So we're going to let that happen. So then we have assertions. So these are database scheme elements like relations or views, the assertion, where we define and we create it by create assertion. And we give it a name, and we do a check on a condition. So the condition may refer to any relation or an attribute in the database scheme. It can refer to anything, actually. So here's our assertion, and we create these assertions and we apply the assertions. So in cells we have bar, beer, and price. No bar may charge an average of more than $5. So we create an assertion, no rip-off bars. And we do a check, and the check says non-existent. Well, what's not going to be non-exist is going to be in here, and this is going to be select bar from cells group by bar having $5 less than the average price. So if the bars with the average price above $5, it can't be in here. That way we can't have rip-off bars. And this is a nice query actually that's showing you, just if you just look at the subquery, it's showing you how to use the group by. So group by bar, but we don't actually we haven't put the aggregate on the select clause. We've put it underneath on the having. So you can put the having can actually have the aggregate average price down here. It doesn't necessarily have to be on the select. So it's a variation of what we've seen so far actually as well. So this is an example of creating an assertion. Here's another assertion where in drinkers we have name, address, and phone number, and bars we have name, address, and license. There cannot be more bars than drinkers. I don't know if that's even possible. But, well, because the bars would go broke anyway. But we don't want any more bars than we have drinkers to fill them. So we can create assertion, few bars, and do a check where it says select count from bars is smaller than or equal to the select count from drinkers. So it'll get to a certain point and then the assertion will click and go, oh, sorry, can't do it. So we can add in, and then it's going to check to see if the count is smaller than or equal to the count from drinkers. If it's larger, then the assertion is going to prevent the inserts. So we put the assertions in there. Every time you do an insert or an update on that table, the assertion gets checked. And then the assertion violates, then nothing ever associated with any of the attributes or even the underlying table. Instead, it gets rejected for some unknown reason, and it's because the assertion failed. Usually there's a message that appears out, but nobody catches it on the console window that says, assertion such and such triggered. So that means rule number something broke, you know, okay. And then you remove the assertion, it works just fine, but then you've just violated all the integrity rules of the database, which defeats another purpose. So timing of assertion checks, in principle, we must check every assertion every time a modification is done to the relation. It doesn't really matter which database relation is being performed on. A clever system can observe that only certain changes could cause a certain assertion to be violated. And so as an example, no change to beers can affect it. Few bars, neither can an assertion to drinkers. So you can have them go on certain table updates and certain table modifications, but not on all of them, as an example. So, alright, so that's the end of the SQL stuff. And just to make sure that you understand the concepts of SQL, what we're going to do next is the last exercise of the weekend. Let me explain something, because some people have already worked on it, and then they've asked the same common questions, so now I have the questions. I'm armed with the questions, so I can answer the questions for you. You don't have to actually put this in a database. You can just look at this information and make assumptions on it. And make assumptions that everything I just showed you in the SQL lecture will work. No need to actually populate, although it's kind of a small table, you probably could if you have it installed. So you see the dollar sign, but this is really numbers. It's not text. So this is 1500, 250, 300, 700 as a number. Assume this, assume these data types. This is a date. This is a number. This is a string. And you're going to essentially write the queries that are associated with each one of the questions. The first set is actually kind of easy, I think. Then 1 through 5 is pretty easy. If you're starting with, let's say for number 6, and you choose this syntax here, and you use the single quotes. If you're using Microsoft Access, you might discover double quotes are needed instead of single quotes. Your queries don't matter whether or not it has double or single quotes, or whether you put the semicolon at the end of each one of the lines. That's not really a concern. What is more of a concern is, do you understand the concept of what it is you're doing? So, as you go through the last part of it, the last question, number 11, refers to both tables. It refers to this table as well as this one up here on the previous page. So you want to use both tables together. And think small on this one. There's no join required. Think about the ends. Think about the unions, the intercept. There's a couple of different ways of doing it, actually, depending upon your style. You can write them all on one line. You can write the queries on separate lines. You can bold and highlight and do everything you want to it. Doesn't really matter. So this one again is due in the EMS by Tuesday evening. This is the last exercise. I'm going to give you some time to work on it, and then we have some concluding lecture stuff. I think, but how long do you guys want on this? 1 hour? Okay, so it's now 2:39, say figure 2:40. 3:40, we'll reconvene for the final and final and final and final lecture for this finally done weekend. Alright, so I'm going to end this video.